what I have presented was the foundation of the scattering theory. So in particular, I derived various expressions for the scattering matrix in quantum field theory. And essentially, I am going to start from the expression which is most useful to us for the rest of this course, namely representation of the scattering matrix as the following time-ordered operator. So S as given by the time-ordered operator S time ordering exponential minus I divided by H bar C integral, four-dimensional integral of the Hamiltonian density, where this HI is a interaction piece of the full Hamiltonian. So interaction piece of the Hamiltonian. And what is important in this formula is that this interaction piece is a time-dependent quantity, where the time dependence is described by the Hamiltonian of the free theory. So this interaction piece of the Hamiltonian is therefore considered in the so-called interaction picture, is considered in the interaction picture, which essentially means that this Hamiltonian density evolves as in the free theory evolves by means of free Hamiltonian. This is what we where we have finished last time. And if you have any questions concerning this derivation or concerning the notion of S matrix in quantum field theory, please ask me.
Sorry, where does time ordering operator come from?
Could you please make it more loud?
Yes. So where does this time ordering operator T comes from? Because last time maybe this is. I remember.
So T ordering operator comes from the way we have solved equation of motion for the Dirac evolution operator. I have introduced the quantity which is called the Dirac evolution operator. Maybe I will just repeat an expression for it, UTT0. So this is a unitary operator which depends on two times, T and T0, and it's given explicitly by the following expression. So free Hamiltonian H0 in the exponential, then another exponential minus I divided by H bar H T minus T0, where H is the full Hamiltonian, and then another exponential minus I over H bar H0 T. So the logic of derivation of the S matrix as a T-ordered exponential was to start from this evolution operator, then write for this evolution operator the differential equation to which it must satisfy, and this evolution equation is of the following form: du over dt is equal to I over h bar v on t u on tt0, where v on t, so time-dependent potential, is now taken in the interaction picture, which means that essentially time-independent potential undergoes evolution with a free Hamiltonian, giving rise to this time-dependent operator v on t, and the differential equation for u on tt0 is then given by this formula, which also it should be also supplied with the initial condition that u on tt0 is equal to the identity operator. If you take this information into account, so this is step number one, first step. Then the second step is to use this differential equation and the initial condition to write for this evolution operator the integral equation. So this is the second step. We have written down for this u an integral equation which follows from this differential equation together with the initial condition, and it looks like this: v on tau integral u on tau t0. This is the second step. And the third step, which we have done, is solve this equation by means of iteration procedure. We solve this equation by means of iteration procedure, where as the first approximation to u, we just take identities, and we take this identity and substitute it instead of u, and then we get a second level approximation, and then we take one identity plus this integral of v as a second approximation and substitute it instead of v to the right hand side again and again and again and again. And at the end of the day, what you will get is exactly the representation which can be compactly written as a t-ordered product of this time-dependent exponential of the time-dependent potential, and that is what we have derived at the end last time. So the time-ordered product comes from implementation of this way of solving this integral equation by means of iterations. So this is where it comes from. Okay?
Okay.
You can look at the end of our previous lecture where I explain in detail, say using the iteration at the second step, how this time-ordered product arises. This is a technical procedure which allows you to represent the final answer for the S matrix in this very compact and elegant form. But in fact, of course, if you do perturbation theory, if you are interested in evaluation of the S matrix, you, of course, understand this exponent in its Taylor expansion. So you write it as a Taylor series, sum from 0 to infinity, 1 over n factorial, minus I divided by h bar c in the power n, and then n-fold integral, dx1 and so on, dxn, t-ordered product of interaction piece of the Hamiltonian, hi x2 and so on. So I here stands for interaction, hi on xn, like this. And so you see that if you want to compute this quantity, the S matrix, you need to understand how to compute this t-ordered product of fields. And since we said that evolution here of HR is due to the free Hamiltonian, this means that at the end of the day, this expression, which is this t-ordered product, reduces simply to the t-ordered product of free fields. For instance, if you have just one field in the theory, say Klein-Gordon theory, where you have just phi on x, then at the end of the day, you need to compute such a quantity, t-ordered product of the field phi taken at different space-time points where the field phi essentially is free. Is free because its time dependence is determined by free Hamiltonian, and that follows from the derivation of the differential equation, or is defined by differential equation for the Dirac evolution operator U on TT0. Now, typically for phi-4 theory, for instance, this potential, this H is taken as phi-4 on x1. So what you will have here will be phi-4 on x1, phi-4 on x2, and so on, phi-4 on xn. So eventually, you need to compute the t-ordered product of a free field, and taken at different space-time points. And in order to compute this quantity, what it means to compute this quantity? Essentially, what you have to do is to bring this t-ordered product of fields to the normal ordered product. Because normal ordered product defines a good operator, because, for instance, when it acts on the vacuum, then the vacuum will be annihilated because all annihilation operators in the normal ordered product of fields are standing to the right. So in particular, if you have such a non-trivial operator and act on by it on a vacuum state, then the vacuum state will vanish. So such an action will be well defined. And in fact, then also computation of various matrix elements of the S matrix will be simple, because your S is already written in the desirable form, where all annihilation operators are standing to the right from all creation operators. So the task, the next task in computing the S matrix elements would be first to bring this t-ordered product of fields to the normal ordered product. Make it normal ordered. And this is done by means of the so-called Wick theorem. So Wick's theorem allows you to rewrite such a t-ordered product of fields where they are normal ordered product. Now, to understand how this theorem works and what it says, it is convenient to start with the simplest example, where I just have t-ordered product of two fields.
I'm sorry, a quick question.
Yeah.
Is it true that we never have differentials of phi's in the interaction part?
Here, you mean here?
Yes.
We can have derivatives. It depends on the form of the Hamiltonian. No problem. We can have.
I mean, the Wick's. We are going to write down Wick's theorem for phi's, not for derivatives of phi's.
It does not matter. Derivatives of phi, since they act on different points in this expression, you can always take them out of the t-ordered product.
So on derivatives, the Wick's theorem works just like on
right,
on
just by how to say, by Leibniz rule. You can just take them out of the t-ordered product, and so it is inherited. If you want to have derivatives, the t-ordered product will be inherited from that of the fields. That would be the right answer to this question. So derivatives, of course, can be, yes. Interaction can be rather complicated. It's not restricted just to the powers of fields. There could be derivatives acting on phi. But say, for instance, if you want to compute the derivative, say, if you want to have here derivative d on x1, then you just consider this as an operator which depends on x1, and then, yes, you can, well, you will see now, actually, yeah. You will see that at the end of the day, I will write this expression for
I mean,
the T-ordered product.
through a Leibniz rule, I can rewrite it as derivative of the whole minus derivative of minus a similar derivative in the second part.
A Leibniz rule probably plays no role here. Sorry, I don't think I said something right. Forget about this. It's just the derivative with respect to the variable x1. So it acts only on the field which depends on x1. It does not act on the field which is at the point x2.
Okay, then it's clear.
Yeah. So let me continue, and you will see how it works. So for the simplest case, we have just two fields, phi on x1 and phi on x2, and we know that a field in the free theory admits an expansion phi plus plus phi minus, where phi plus and phi minus are positive frequency part and the negative frequency part. And the positive frequency part comes with a creation operator. So it's 1 divided by 2 pi 3 over 2 prefactor, and then integral with this measure to k0. So k0 is equal to omega on k, a dagger on k, and exponential I k0 time minus I kx, right? So this is what we call positive frequency part, and there is the negative frequency part, which is phi minus. A on k, and then minus I k0 t plus I kx. K0, as I said, is that's just k squared plus m squared, the same as frequency, and this is positive. This is positive quantities, so k0 bigger than 0. Like this. Okay. Therefore, from these expressions, we see that if we act by phi minus on the vacuum state, we obtain immediately 0, right? Because this piece of the field contains annihilation operator. And the conjugate expression to this section is left vacuum annihilated by phi plus on x. Now consider the situation where x0, so time of the field depending on x, is bigger than y0, where y0 is a time variable of the field phi on y. Then T-ordered product of phi
I'm sorry.
x.
I'm sorry. By the vacuum here, we mean the vacuum of the free theory.
Of course. Everything now is written in terms of free fields, in terms of free oscillators. This is a time evolution which is induced by the free Hamiltonian, and so everything is here is free. And that's why perturbation theory is manageable, because we have written down the interacting the quantities in the interacting theory only with those of a free theory. And that's why we can allow ourselves to make these computations. The information about the interaction now sits in the expression for this Hamiltonian HI in terms of these free fields. For instance, if this is a phi 4 theory, then this HI is a field phi in the power 4. But this field evolves freely. That means by means of the free Hamiltonian. If you would have another interaction, if you would have another interaction, say phi 6, then you have to use here instead of H phi 6. But still, evolution goes with the help of the free Hamiltonian, and that's why I'm using here expressions for the free fields and also free field vacuum. Okay, and so now what we do? We say x0 is bigger than y0. This means that I should write this t-ordered product as phi x and phi y, right? Because x0 is bigger than y0, so field phi on x is older. And that's why, according to the time ordering, it goes to the left from phi y. And now I expand these fields in terms of positive and negative frequency part. So phi plus on x plus phi minus on x, multiplied with phi plus on y, plus phi minus on y. Then let's open the brackets and get phi plus on x, phi plus on y, plus phi plus on x, phi minus on y, plus phi minus on x, phi plus on y, plus phi minus on x, phi minus on y. Let's look more closely at this expression. What do we see? We see that this expression depends only on creation operators, and here we cannot do anything. These are all creation operators, and the creation operators commute between themselves. Here, the expression depends only on annihilation operators, and this is okay, so it's already normal ordered. Here, annihilation operators tend to the right from the creation operator, and then this term is already normal ordered. And the only term in this expression which is not normal ordered is this one. Right? Because this term is such that the annihilation operator in phi minus tends to the left from the creation operator in phi plus. But I can normal order this term by doing the following. I can rewrite it in the following way. Okay, let me make black. So I can say that this is phi plus on x, phi plus on y, plus phi plus on x, phi minus on y, plus, and here I put these fields in a different order. So I write phi plus on y, phi minus on x. But in addition to that, I will add the commutator of phi minus on x, phi plus on y. So if I open this commutator and write it explicitly, you see that the term phi minus on x, phi plus on y will be restored back. This will be restored back, and the term phi plus on y, phi minus on x will be cancelled with this guy. So in other words, I added and subtracted the normal ordered field, and that's why I produce as a result this commutator. The fields which are here are already all normal ordered. I think I also need to add to this phi minus on x, phi minus on y, which is already normal ordered. So these fields are normal ordered, and therefore I can write this expression as follows. I can say that I normal ordered my fields, so they go under the sign of normal ordering. And under the sign of normal ordering, you know that you can actually put the fields in any order, because the fact that you are writing sign of normal ordering means that from this product, so this product operators creation of creation annihilation should be ordered exactly according to the normal ordering rule. And that's why I can again put the fields in the order I like, and I like the order which they have in the original expansion. Like this. No, and then there will be also a commutator phi minus on x, phi plus on y, and we know about this commutator, that this commutator is actually a C number. In other words, this is a function of x and y multiplied by the identity operator. And so this, for this reason, because this is C number, this commutator can be taken out of the normal ordering. And then under the sign of normal ordering, you see the usual product of fields, phi on x, phi on y, normal ordered, plus the commutator phi minus on x, phi plus on y. Okay, so this is what you will get. Once again, the normal ordering sign here means that you have to multiply the fields, and then you have to arrange in the product the operators of annihilation to be on the right from all the creation operators. Analogously, you may consider the case where y0 this time is bigger than x0. And you can repeat the same computation. So this time, if you write the ordered product of phi on x, phi on y, then this is phi on y multiplied by phi on x, because phi on y is an older operator, so it stands from the left from phi on x. Then again, you write all the fields where positive and negative frequency part, and you use the same trick of ordering fields according to the normal ordering prescription. And as a result, you will get a commutator left over. So at the end, the result is written again as a normal ordered product of phi on x with phi on y, plus this time the variables x on y interchange. So you get phi minus on y, phi plus on x. To summarize, yeah.
So shouldn't it be phi y and phi x in normal ordering?
Again, normal ordering, it does not matter in which order you write. It does not matter, because fields under the sign of normal ordering commute among themselves. Because as soon as you put the fields under the sign of normal ordering, this means that when you would like to write them as an explicit operators acting on the Fock space, you always have to write them in such a form that all annihilation operators should be to the right from all the creation operators. So it does not matter how you write the operator, in which order you write the operators under the sign of normal ordered product. This sign tells you that when you write it as an explicit operator, all the annihilation operators should stand to the right from creation operators, regardless of how you write the fields, what order of the fields are under this normal ordered product. I can equally write it as a phi on y, phi on x, does not matter. Under the normal ordering, sign the fields commute, because the result of evaluating of this normal ordered product will be the one and the same, regardless of in which order you put these fields.
Okay.
Is it okay? Okay.
Yeah.
Okay. But again, the difference between the actual T-ordering product and the normal ordered product, as you see, comes in these terms, in the appearance of these additional terms, which are commutators and which are C numbers. So in other words, to summarize, what we have obtained is that we obtain the following, that, okay, so to formulate what we have obtained, I need to introduce one more convenient notion, namely the notion of a pairing of two fields. So in other words, if you have two fields, phi on x and phi on y, I define an operator of pairing, or it's also called contraction. Maybe contraction is a better word. Contraction of the field phi on x and phi on y, which is equal to the commutator phi minus on x, phi plus on y, if x0 is bigger than y0, and it equals to phi minus on y, phi plus on x, if the time variables satisfy an opposite order. Okay, so this operation is called contraction. Contraction of pairing of the fields. And if you now look at this expression of what is the contraction, you realize that this contraction is nothing else as a Feynman propagator, because you can write down this contraction as a single formula by saying that you have theta function x0 minus y0, and then you have phi minus on x, phi plus on y, plus theta, y0 minus x0, contraction, phi minus on y, phi plus on x, like this. And this is, by definition, if you look at our course, at our previous course, then this is nothing else as a Feynman propagator, delta x minus y. So pairing of the fields is just a Feynman propagator, which means that now we have found a nice relation between T-ordered product of two fields and the normal ordered product. So T-ordered product phi on x, phi on y is equal to normal ordered product of these two fields, phi on x, phi on y, plus pairing phi on x, phi on y, which is, as I said, nothing else as a Feynman propagator. And since Feynman propagator is C number, what I can do, I can actually write everything what I have here under the sign of normal ordered product. Because this is C number, it can get out of the normal product, and can get in, it can get out, because this is just a C number. So this is a Wick theorem, and this is exactly the Wick theorem for two fields. Just for two fields. In other words, yes, in this context of just two fields, this theorem is telling that T-ordered product of two fields is given by the normal ordered product of these two fields plus a contraction of these fields. And now I can generalize this theorem for the case of any number of fields. For any number of fields, this theorem states that T-ordered product phi on x1 and so on phi on xn is equal to the normal ordered product of these fields, phi on x1 and phi on xn, plus all possible contractions, plus terms with all possible contractions on these fields. All possible contractions. And this is a statement of the Wick theorem. So very compact expression. T-ordered product of any number of fields is given by the normal ordered product of these fields with all possible contractions. Before I prove this theorem, before I indicate the proof of this theorem, let me give you an example, a simple example. So suppose we have four fields. And in order for me to how to say to explain this in a compact way, let me just denote phi on xi, phi depending on xi. Let me just say that this is phi I, and not to write an argument explicitly. So if you have, for instance, 4 fields, phi 1, phi 2, phi 3, and phi 4, then this theorem says that T-ordered product of these fields is normal ordered product without contractions. This is the first term, without contractions. Then there will be terms where you have just one contraction. And there will be 6 such terms. So phi 1 with phi 2, contraction plus phi 1, phi 2, phi 3, phi 4, phi 1 with phi 3, phi 1 with phi 4, phi 1, phi 2, phi 3, phi 4, 2, 3, and 1, 2, 3, 4, 2, 4, plus 1, 2, 3, 4, 3, 4, plus now there will be terms with double contractions, because theorem says all contractions should be performed whenever they can be performed. So contraction between 1, 2, 3, 4. There could be a contraction 1, 3, 2, 4, like this. And finally, phi 1, phi 2, phi 3, phi 4. There could be contraction 2 with 3 and 1 with 4. That's it. Now, when we contracting these fields, these contractions can be replaced by the corresponding Feynman propagators. And you see that what you will be left with are the 4 fields which are normal ordered product. This is this. Then the fields which contain only 2 non-trivial fields entering. This is when one contraction is performed, replaced by the Feynman propagator. And there will be also fully contracted fields which are just products of Feynman propagators. Okay, so this is what we obtain for the case of 4 fields. Now, for instance, we can write just to be even more explicit. If we have, for instance, phi 1, phi 2, phi 3, phi 4, and we are contracting, say, phi 2 and phi 4, then this produce a propagator x2 minus x4, and leave behind the normal ordered product of the fields phi 1 and phi 3, like this. Moreover, such rearrangement of T-ordered product in terms of normal ordered product of fields allows immediately to compute the vacuum expectation values. For instance, if you put the T-ordered product of our 4 fields in vacuum, so phi 1, phi 2, phi 3, phi 4, in the vacuum, so what we compute is the vacuum expectation value, as it's called, then the result will be according to this expression here, simply given by the fully contracted terms. Because in all the other terms which are left over, you always have annihilation operators. And since you have annihilation operators, they're already standing to the right from the creation operators. And that means that acting on the vacuum, they will immediately produce 0. So all the terms without without being fully contracted, they produce 0 contribution. And then you can easily read off what is left over from these terms. So from the first term, you get a propagator delta x1 minus x2. Second gives you delta x3 minus x4. So this is this term here. Then this term will produce for you plus delta x1 minus x3 delta x2 minus x4. And finally, the last term will give you delta x1 minus x4 delta x2 minus x3. I guess it makes clear how this theorem works, right? And if you would like the formal proof why this is valid for any n, for any number of fields, you can use the mathematical induction. So mathematical induction is probably the simplest way to prove the general formula. So assume that the theorem, Wick's theorem, is true for m minus 1 fields. This is assumption of the induction. So m minus 1 for m minus 1 fields. Wick's theorem is true. And you need to prove it for m fields. Yeah, for m is equal to 1 and m is equal to 2, it works. That we can check by explicit calculation. And then we assume that it works for m minus 1. And we have to prove now that it works also for m fields. And without loss of generality, we can consider one of the cases of time arrangement. So for instance, you can take an arrangement where the time variables have the following ordering. So you consider for the first field, say x1, x1 0 is bigger than x2 0, and this is bigger than x3 0, and then this is bigger than xm 0. But of course, you can take any arrangement you like. I pick up this one. Then you can write t-ordered product of these fields, phi1 and so on, phi m. You take m fields, and according to the time variables, this should be equal just to the normal usual product of these fields. Yes, according to the time ordering. And this you may write as phi1, and then replace the product from phi2 to phi m by t ordering product of these fields, right? Because they already time ordered. They already time ordered, and adding this sign t does not do anything. Now we can apply Wick's theorem to these m minus 1 fields, which are under the time ordering, and that will give me the following. So phi1 I split into creation part and annihilation part, and this time ordering will produce for me just normal ordered fields phi2, phi m, like this, plus all possible contractions. Fields with all possible contractions, not involving phi1, simply because phi1 is absent among these fields phi2 and so on phi m. So here, this is where I'm using induction assumption, and I'm making induction step, trying to prove that this will be valid for any m. Now here, the field phi1 plus can be moved inside the normal ordered product because it depends on the creation operator only. And in these normal ordered expressions, in the curly brackets, all the fields are already ordered in such a way that all creation operators are standing to the left. So there is no problem to put this phi1 plus inside. While for phi minus, you have a problem because phi minus contains annihilation operator, And now this annihilation operator, for instance, meets this normal ordered product of phi 2 and phi m, right? Where under the normal ordered product implies that all creation operators stand to the left. And so this creation operator meets annihilation operator, which is in phi 1 minus. So you say, okay, then what you can do? You can say that you commute this phi 1 minus through all operators phi 2, phi m, and write it like this. But of course, you have to add up the compensating contribution, which is a commutator of phi 1 minus with all normal ordered product of operators phi 2, phi m, right? So this is identity, which I have written down. So for the moment, I have not done nothing. This is an identity. And then in each of these fields, you have a creation operator. And they will be always standing to the left. But under normal ordered product, that does not matter. I can put them in the original order as they sit in the fields phi 2 and phi m. And therefore, what I will be getting here is simply this first term with which I do nothing, phi 2 and so on, phi m, plus commutators, phi 1 minus with phi 2, phi 2 plus, because from phi 2, only phi 2 plus containing the annihilation operator, containing the creation operator will not commute with phi 1 minus, and then phi 3 and so on, phi m, plus and so on up to phi 2 and so on, phi 1 minus with phi m plus, right? So in other words, I will commute phi 1 minus with any of these fields phi 2 and so on, phi m. But this is what is written down here is nothing as the normal ordered product of phi 1 minus, phi 2 and so on, phi m, plus all possible pairings of the fields. Yeah, I can even write everything under the same sign of the normal ordered product. So phi 1, phi 2, and so on, phi m. Sorry. And sign of contraction, say of phi 1 with phi 2, and so on, up to contraction of phi 1, phi 2, and so on with phi m, under the sign of normal ordered product. Now, very similarly, phi 1 plus or phi 1 minus will be contracting with terms corresponding to all possible contractions not involving phi 1, because these terms, they have partial contractions, so they have also free fields with which phi 1 minus should be contracted. And so at the end, you will produce all possible terms involving a single contraction of phi 1 with one of these fields. So in other words, doing this with all the terms, you eventually get all possible contractions of all the fields, including phi 1, meaning that by this you just finish the induction step and you prove that the Wick theorem now works for m fields if it works for m minus 1 fields. Okay, is it idea of this proof is clear?
Yes.
Yes, kind of.
Mm-hmm. Yeah, you may try to play a little bit with it yourself, and then you can easily see that this can be done in the way I just explained. Now, what is nice about the Wick theorem is that it can be written in the concise functional form, which is very convenient for practical calculations, and I think we will meet it later on, or might meet it later on. This is the following form, functional form of Wick's theorem. And this is the following thing. So T-ordered product of the fields phi on x1 and so on phi on xn can be computed in this way. It's a normal ordered product of what? Of the following operator, 1 over 2 delta phi. I will explain what is this. Propagator delta phi. And then there is a product phi on x1 and so on phi on xn. Where these fields phi on x1 and so phi on xn are considered as classical fields, not as operators, but just as classical fields, and where after the computation of this operator, exponential operator acting on these fields, you have to substitute classical fields for operators and normal order them. Where this functional expression is understood as the following double integral: dx dy delta phi x Feynman propagator x minus y delta phi on y. So this means that in order to compute the action of this exponential operator on the fields, you take this exponential, you expand it in a Taylor series, and then you start to apply these operators term by term to the product of the classical fields. And then at the end, when this computation will be done, when all fields will be exhausted by the application of derivatives, you replace what is left over, the expressions for phi, by the corresponding operators, and everything will be under the sign of normal ordered product. And whatever you apply such an operator to the product of two fields, you will get an appearance of the Feynman propagator. Now, practically, say, for instance, if you take phi on x1, phi on x2, let's say practically, so what do we get if we apply such an operator, say, to the product of these two fields? You will get integral dx dy, and then you see that first time this delta phi can be applied to phi on x1, and then it can be applied to phi on x2. So basically, this derivative, functional derivative, acts, of course, by the Leibniz rule. So you will get delta phi on x, delta x minus y. And then you will get delta phi on x1, delta phi on y, phi on x2, plus phi on x1, delta phi on x2, delta phi on y, right? And this gives you, of course, a delta function, x1 minus y. It's a classical field, so you consider this phi on x1 as a function of x1. You vary it with respect to the same function on the variable y, so you get delta function x1 minus y. Here you get delta function on x2 minus y. And then you apply another variation. So propagator is left over. So you get, let's do the second variation, dx dy delta x minus y will be left over. And this will act first on this, and then it will act on this term. So you will get delta function x1 minus y. This is this one. And the application of functional derivative with respect to phi and x will produce another delta function, x2 minus x, plus delta function x1 minus x, delta function x2 minus y. Then you integrate with respect to x and y. You get propagator x1 minus x2 plus propagator the same x1 minus x2. So it doubles. But on the other hand, you see there is this coefficient 1/2 standing in front. And this exactly stands for a purpose to cancel out this 1/2, this 2. So they cancel, and at the end you get, as a contraction of two fields, just a propagator delta x1 and x2. And you can also see that very nicely when you expand this exponential, from exponential you get 1 over n factorial at n soda. This n factorial exactly matches the number of repeated terms which you will obtain upon applying n times this variational operator to reproduce you exactly the right number of terms which is in this formula for the Wick contraction. For instance, if you want two contractions, you get here 3 terms, 1, 2, 3. And these 3 terms will appear because upon evaluating application of the of this functional operator in the second order of expansion of exponential, the corresponding term 1 over 2 squared exactly produce for you the right number of terms, namely 3, which you act in the actual Wick theorem. So this is very convenient form of the Wick theorem, which finds application also in the functional methods of quantum field theory. And so it's very useful to remember it. Any questions here? I'll show you now in practical how practically it works, or how it works in practical computations by computing, for instance, the following quantity. For instance, you need to compute T-ordered product of fields which are already partially normal ordered. Say, for instance, phi on x in the power m, and say phi on y in the power n, like this. The essential point which concerns such expressions is that if the fields are already under normal ordered product inside the T-ordered product, then you don't need to take contractions of these fields among themselves. In other words, if you have fields which are already normal ordered inside, or partially normal ordered, say phi n plus 1, say phi on xn plus 1, and so phi on xm. When you will be computing the T-ordered product of such partially normal ordered sets of fields, you don't need to take contractions between the fields which are under the sign of normal ordering. What you need to do, you need to take only contractions between the groups of these fields which are between the groups which contain fields, and only these contractions should be taken into account. But you don't need to take contraction between the fields which already sit under the sign of normal ordered product. Because these contractions would not produce you propagator, for the reason that fields they are already normal ordered. So they are already normal ordered. So you don't need to, even if you write them in terms of T ordering product, since they are normal ordering put you back in the situation where all creation operators will be standing on the left from annihilation operators. So that means that you don't need to take contractions within the one and the same group. And so, for instance, you are asked to evaluate such T-ordered product of, say, phi in the power m. So field phi on x is taken at the one and the same point x m times, and the field phi y is taken n times under the sign of normal ordering problem. So you apply our functional formula. Let's denote this phi on x by x capital. So x capital in the power m. Let me not to write letter x. It's clear that this is depends on y. This is capital X. And field phi on y I denote as y, capital Y on n. So I need to evaluate such a thing. And I apply the functional formula. So I expand exponential 1 over k factorial. And then there is 1/2 delta delta phi propagator delta delta phi in the power k. And it's applied now to sort of classical product of these fields, xm and xn. And I know that I don't need to apply this operator to two x's or to y's or to two y's, because these fields are already under the sign of normal ordered product. So I need to apply it in such a way that one leg of this functional operator acts on x, and another leg of this functional operator acts on y, right? And so the result of this will be, well, starting from k0 term, k0 is identity. So I don't do anything. So this will be just xm, y, n, nothing. And the other terms will be as follows. So sum from k is equal to 0, no, up to infinity, up to what? Up to n. Yeah, we will see up to what? Delta in the power k divided by k factorial. And now from m axis, the number of ways I can I can pick up one x is m. Then I have to pick up another x, and this will be m minus 1 times, and so on, up to m minus k minus 1. And concerning y, this will be n minus 1, and so on, up to n minus k minus 1, like this. And let's assume for definiteness that m bigger or equal to n, just to make this formula even more concrete, because then this sum here will run, will stop at k equals to n, because n is smaller than n, and I will be exhausting the index n by acting on it, by acting on the fields yn by more and more derivatives. And so the number of times this will be done is n and minus 1, and so on, up to n minus k minus 1. And so the last value of k where I can apply it is k is equal to n. I think it's clear. And what will be left over after k applications is x in the power m minus k, because k fields go to pairing. And from y, n minus k fields go to pairing. And so this is a formula, but then, of course, you know that what is written down here is nothing else as m factorial divided by n minus m minus k factorial. This is n factorial divided by n minus k factorial. And therefore, what you get here is sum. Let me write. I don't think that this is written down correctly here, this is k is equal to 1, because I think the first term corresponding to k is equal to 0 I'm taking out. And therefore, if I combine, now they will be sum from k is equal to 0 up to n. All right. What I can do, I can also multiply this by k factorial, and I can divide it by k factorial, k multiply by k factorial, k divide by k factorial. This is I do in order to get binomial coefficients. And 1k factorial cancels out, so I will get delta in the power k, binomial coefficient m choose k, binomial coefficient n choose k, and then x in the power m minus k, y in the power n minus k. Yeah, this is how it works. So this is, I represented the t-ordered product of such powers of fields in terms of normal ordered product of these fields. Okay. Now, we can go on and actually try to compute the S matrix, at least at the leading order of perturbation theory. For instance, for the interacting field, taken as the simplest example, say complex scalar field with self-interaction, and compute a two-body S matrix at leading order of perturbation theory. And we can further use this result, for instance, to evaluate such a physical quantity as a cross-section. And the considerations of this type, which I'm going to present, they are actually very common to any other theory, including, for instance, quantum electrodynamics. In principle, you, when you compute this matrix, you will be doing the one and the same thing. And complex scalar field provides a nice arena to understand to understand in detail how the evaluation of the scattering matrix works. So let me sort of briefly explain or start to explain how this can be done. So the theory of a scalar field, complex scalar field, is very similar to the usual real Klein-Gordon field. So the action is given by dx 1/2 d mu phi star. So phi is a complex field, and phi star is complex conjugate, minus 1/2 mc over h bar, the mass term phi star. And we may include a self-interaction of this field in the form g coupling constant divided by h bar c, phi star squared. This is non-trivial term, which I call self-interaction. The field interacts with itself. G here is dimensional coupling constant, and h bar c sits for dimensional reasons in order to make every term in this action to have the one and the same physical dimension. It is very convenient to make a rescaling, and this is what people usually do, to rescale field by this square root of h bar c. By the way, let me remind that this quantity h bar c has a physical dimension of electric charge. If you do this rescaling, then the action starts to have an explicit prefactor, which is just h bar c, and that stands in front of the action, in front of the integral, in front of the integral, and integral itself is a dimensionless quantity then, because we know that action must have dimension of h bar. So what is now written down is a expression which is dimensionless, g over 4 factorial phi star squared. So this is a complex scalar field. Now, again, you can expand this field phi in terms of creation and annihilation operators. That's done exactly the same as for the case of a real field. So c in the power 1/2. Again, these prefactors like speed of light are not so important for us. We can work in natural units if we wish. Omega, and then annihilation operator, wave, plus b dagger on k. And I will comment on this, omega t minus kx. And phi star. Very similar. So fields are time dependent. B on k here, exponential minus I omega t minus kx, plus a dagger on k, I omega t minus kx.
So,
Yeah.
Do we also have some higher order terms other than phi star squared?
No. It's just enough to consider this interaction phi in the power 4, which is essentially it's a modulus squared of phi squared.
But this we can also treat it like as a perturbation, right? The field.
Yeah,
Because
yeah.
of
So
the
this is what I'm going to do. Actually, I'm considering. I mean, the expansion in terms of powers of potential or in powers of interacting Hamiltonian, as you see, that's essentially the same as expansion in the powers of this coupling constant, because the coupling every power of the interacting piece is supplied or goes along with the 1 power of the coupling constant. So S matrix expansion in terms of in powers of this interaction potential, which is this quantity here, this is interaction potential, goes along with an expansion in powers of coupling constant. Yeah.
So according to if we treat it like some perturbation, then shouldn't there's some higher order terms, or we're ignoring it because they are very small?
No. In general, you should not ignore them. In principle, yes. So perturbation theory is an infinite series, right? It's an infinite series. But if you say that your coupling constant is small enough, then every next term should provide a smaller and smaller contribution to the scattering process, right? That's an idea of having the coupling constant to be small.
Yes. It's like, so for example, if we have some very highly interacting theory, like in nuclear force, for example, thermodynamics, so there we should not ignore some higher order terms, right? Only
exactly. In that case, we would have a trouble with setting up the perturbation theory. That's absolutely true. That is very true. Yes, what you are saying. There are various reasons why perturbation theory can fail. There are various reasons for it to be fail, or at least at a certain point in the expansion in the coupling constant. That's right. And for instance, so in fact, saying simply that perturbation theory is true or fails is not the right way to pose such a statement or such a question. One has to specify in which regime this coupling constant, this perturbative expansion is true, or it holds or it fails.
yeah.
So things are much more complicated that I'm trying to, to explain in this example. And this is, of course, related to the certain phenomena which we have not yet discussed. So for my practical reasons, what I want to say now is that we can just apply this formalism which we have developed. I mean, the expression for the scattering matrix as a time-moderate product of interaction potential and the Wick theorem, we can apply to practically compute the matrix elements of the S matrix in perturbation theory, for instance, at leading order in perturbation theory. And why I'm talking about complex scalar field here, not about the real field, is just because the complex scalar field in a way contains antiparticles. It contains particles and antiparticles. So what I want to say that because it's complex, it contains now the operators A and A dagger, which annihilate and create particles. So these two operators particles, so correspond to particles, and these operators B and B dagger, they correspond to antiparticles. No, it's the simplest theory where you can say you can have both particles and antiparticles. So this theory is simpler than, for instance, Dirac theory, where you have electrons and positrons, because in that case, the particles are spinors. In our case, they're just scalar particles. So from this point of view, they are simpler. And if you quantize the corresponding field, of course, you find the standard commutation relations between creation and annihilation operators. This would be delta K minus K prime. And for B's, it's the same. Delta K minus K prime. All the other commutators are equal to 0. And S matrix will be then given by T ordered product exponential of this interacting potential. So what we will get is I, H bar, I think it will cancel, G over 4 factorial integral dx. So this is 4-dimensional integral over space and over time, so over space time, phi star squared normal ordered. So I take this interacting Hamiltonian or interacting potential already in the normal ordered form. That is convenient. That's a bit convenient because it prevents me from taking the normal ordered, taking pairings within the potential itself, within the point seat, within the field sitting at the one and the same point. So it's convenient to define the interacting part of the Hamiltonian already in the normal ordered form. No, and then you may pick up external states. Since you want to compute the matrix elements of the S matrix, you need to sandwich this operator S between states. And so you pick up asymptotic states, which are characterized by the presence of several particles whose momenta I denote as K1 and so on, K, say A, and say antiparticles, which I denote, whose momenta I denote as P1 and so on, PB, like this. And so this is a state, and if I want it to be Lorentz invariant, I have to write it with a certain prefactors. I think we discussed this prefactors in our quantum field theory 1 course, like this. Another one from 1 to B, 2 pi in the power 3 over 2 square root of 2 omega on p, pj, and then creation operators which act on the vacuum, on the Fock vacuum. So what you see here is a state in the Fock space which contains A particles and B antiparticles, like this, acting on a vacuum. So now we take this as matrix and expand it in powers of this interaction term, which essentially means that we are expanding in powers of G. So S first starts from identity, then there will be first order, second order, and so on. And so if you restrict yourself to the first orders, then the first order in this expansion will be given by this integral, ig 4 factorial integral dx phi star squared. The second term, it will produce for you 1/2. That comes from the exponential, ig squared divided by 4 factorial squared integral dx dy, and then t-ordered product of what? Of phi on x, phi star on x squared, phi on y, phi star on y squared, and then it's closed. And so high terms will be given by t-ordered product of high terms in the expansion of this exponential operator. Okay, so this is how these terms look like. And if you are interested, just say at leading order in perturbation series, then you have to restrict yourself to just T1, yes, first order in the Kaplan constant. And now in this expression for T1, you have to substitute the expressions for phi, which I have written down. So you need to substitute these two formulas for phi and phi star. The simplification which we get at leading order of perturbation theory is that we don't need to evaluate t-ordered product. That's why I take this, t-ordered product is trivial because the object, the potential, I've taken already in the normal ordered form, so there is nothing to normal order in this expression, and you don't need the Wick theorem even to evaluate it. So what we do is we write T1 now by plugging inside expansion of our fields phi and phi star in terms of oscillators. And that's produce pretty long expression. So that's because every field contains two oscillators, and you will get the integral over dx. You will get an integral over, you see here, in fact, you have 4 fields, right? Because of the square, you need to substitute field phi 4 times. And field phi and phi star is given by integral over momentum. So you will get 4 integrations, dk1, dk2, dk3, dk4. So 4 integrations. And from each measure, you will get the corresponding 2 omega on k1, 2 omega on k2, 2 omega on k3, 2 omega on k4. And then fields. So which means you get normal ordered product. The first field, A on K1, exponential minus I K1X. I write it now, this product in the relativistic form. So k1 multiplied by x, this is a product of 4 vectors. B dagger on k1 exponentials I k1x. Another field, B on k2 multiply with exponential minus I k2x plus A dagger on k2 exponential I k2x multiplied 2 more fields and another one is B on k4 minus A k4x plus A dagger k4 I k4x. Okay, this is what you get at this order. And so now if you open all these brackets and write this expression in the normal ordered form, how many terms you will get? You will get 16 terms, right? 2 cross 2, 2 from here, 2 from here is 4, by 2, 8, and by 2, 16 terms. You will get 16 terms. And these terms, product of these two, of any of these oscillators, will be accompanied by the corresponding by the product of the corresponding exponentials which they contain. And these exponentials we can integrate because they do depend on the variable x here, and the x involves integration over time and also integration over space. Then integrating such exponentials containing the product of relativistic vectors, of 4 vectors, you will start upon integrating, obtain delta functions. And for instance, let's concentrate on one of the terms of these 16 terms. Let me not to write this prefactor, but just to write the result of integrating over x. Maybe I will not put equality here, but just indicate one of the terms. So let's pick up, say, for instance, oscillators A depending A on K1, A on K3. No, let's say B on K2 and B on K4. This will come with exponentials. A on K1 will contain exponential minus I K1x. AK3 will contain minus I K3x. Then B on K2 will contain minus I K2x. And B on K4 will contain minus I K4x. So here you see x I can take out. Let's take x out. I we can also take out. So write this as minus K1 plus K3 plus K2 plus K4, and the bracket is closed. Then, as you see, we can perform integration over x of this exponential. It will give us delta function, and this delta function now splits in the delta function describing the conservation of energy that corresponds to K1 0 plus K3 0 plus K4 0 and plus K2 0 equals to 0. And then the conservation of 3-dimensional momentum. So these terms, therefore, will be accompanied upon integration over x by the following prefactor by the following coefficient. Delta function k1 0 plus k2 0, this is k2 0 plus k3 0 plus k4 0, and also three-dimensional momenta, like this. No, and then the rest, of course, will be left over. So if you take outside 2, 2, 2, and 2 here, so you will get a prefactor I G C in the power squared divided by 4 multiplied by 4 factorial. And then from delta function, you get 2 pi in the power 2. Right. And I missed here also a prefactor from these fields, which is 1 over 2 pi in the power 6, to be exact. And so this will be one term, which comes with integrations over 3 momentum. Divided by square root omega on k1 up to omega on k4. And in this expression, you know, when we solve the equations of motion for free fields, this k 0 is in fact omega on k, and omega on k is fixed in terms of space momentum. So in other words, k0 for any of the fields I is omega I depending on k, three-dimensional vector k, divided by c. And this quantity is bigger than 0 always. You know, this quantity for relativistic particle is k squared plus m squared. So if m squared is equal to 0, this k0I is always positive. But since it's always positive, you see that this delta function, which renders the conservation of energy in the scattering process, you can treat it in this way, just tells you that the configuration where sum of the energies of these 4 particles is equal to 0, in order for this delta function to be realized, is not possible. Because k1 0 is positive, k2 0 is positive, k3 0 is positive, and k0 4 is positive. And as such, then this delta function never contributes. And therefore, the corresponding contribution of this product of these 4 oscillators just decouples for the reason that this is a kinematic configuration which can never be realized. And so this is the way you have to analyze all 16 terms which come out from this product. And what you right? Yeah, question?
Yes, here. So k0 here corresponds to energy, right?
Yeah. So that's exactly the energy. Yeah.
Yes, for example, yes, I understood that it has to be positive. But example, if it's an antiparticle, then its energy is negative always.
No. Here energy is always positive. Energy is always possible. So antiparticles here, these are objects which carry an opposite charge. They're charged positively, but the dispersion relation for them is still the same. Because it's a quantum field theory. It's like for the Dirac field, antiparticles have the same positive energy, but they have negative charge. They have opposite charge with respect to particles. Okay? There is no negative energy here whatsoever. Right. And so you have these 16 terms, so you have to write them very accurately. And I do this in the lecture notes. You can have a look. I'm writing explicitly all 16 terms. And when you analyze them from the point of view of conservation laws, to see where this conservation laws arising from integrating the exponentials admit the corresponding term to be non-zero, you will end up only with 6 non-trivial terms. And these 6 non-trivial terms are the terms where you have delta functions of this sort. So 2 particles with positive energy gets in, and the conservation law, for instance, tells you that 2 particles are getting out, and the conservation law is written like K10 plus K20, so energy of the incoming particles is equal to the energy of the outgoing particles. And this comes with various combinations, K10 plus K10, K10 plus K30, minus K20 minus K40, and so on. As you see, there is the number of these 2 particle in configurations and 2 particle out configurations is exactly 6. No, because from 4 momenta you can pick up 4 times one of the momenta, and to make a second incoming particle you have 3 choices. But then since it does not matter how to write K10 plus K20 or K20 plus K10, you need to divide by 2, so you will be left with just 6 non-trivial delta functions, which are allowed by conservation laws, No, and after that, you sandwich the corresponding expression for these 6 delta function, for these 6 terms between the states. Well, maybe I will write down the intermediate result. So the intermediate result, when you make the proper change of variable, the 6 terms get into 3 terms, and this T1 operator, which is allowed by the corresponding conservation laws, will take the following form: IGC squared 4 factorial 2 pi squared integral dk1 up to dk4. Here, delta function k10 plus k20 minus k30 minus k40. This is upon I do the change of variables in order to bring all these delta functions to the one and the same form. Divided. And again, I write here with 2 omega k1 up to 2 omega k4. Here I will be left over with the following oscillators: A dagger on k1, A dagger on k2, A on k3, A on k4. So this contains only particles. So there will be term which contains only particles. Now there will be term which contains only antiparticles. Very similar like this, but now with only antiparticles. Exactly 2 coming, 2 outgoing. And there will be 4 with coefficient 4, the mixed term of the following type: A dagger on k1, A on k3, B dagger on k2, B on k4. And that's it, what is left over. And I've written this result in the normal ordered form. As you see, all creation operators on the left. Here, A and B dagger commute, so it does not matter. B dagger can be put to the left from A because these 2 are commuting, so it does not matter. And this shows that actually the matrix elements of T1 will be only between the states which look the following. So non-trivial matrix element arises for a state which contains 2 particles only. So AA means particle-particle, which is 2 pi cubed and then square root 2 omega on k1 2 omega on K2, like this, and then particle, another particle, 0. State which contains particle and antiparticle. I call it A and B. So A is particle, B is antiparticle. The same normalization prefactor. A dagger on K1, B dagger on K2. No, and finally, there will be non-trivial matrix element between for a state which contains only antiparticles. So BB state, let's call it BB state. 2 pi cube, exactly the same prefactor. And then twice B dagger. Now, what you can do, so this is exact result for T1. For T1, this is exact result. All the other terms decouple because they are prohibited by the corresponding delta functions. They never realize, its kinematic configurations never realize. So this is complete T1, which we can now sandwich between the states, because only between the states, due to the structure of these interaction terms containing 2 creation and 2 annihilation operators, it is clear that the only non-trivial matrix elements for T1 will be the following. So K3, K4, K3, K4, T1, and this we take for AA, particle, particle, K1, K2, particle, 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 AA. So it turns out that this amplitude, this matrix element, will be the same as if you do the sandwich in this operator between BB, T1, K1, K2, BB. Oops. Okay. Like this. And finally, it turns out that this is still the same if you sandwich T1 between states which are containing 1 particle and 1 antiparticle. So all the time you will discover the one and the same amplitude, AB, like this. Where this amplitude, say AA, K3, K4, T1, K1, K2, AA, will be given by the following expression: I 2 pi in the power 4, delta function, which describes the conservation law. So sum of all incoming momenta is equal to the sum of all outgoing momenta in the 4-dimensional sense, so momentum and energy, and then multiply by the factor which proportional to the coupling constant. So this number here at leading order, that's the matrix element of the S matrix at this order. And I just demonstrated for you how it is calculated, how it is calculated in the explicit, in an explicit way. So initial K is K1 plus K2, outgoing K is K3 plus K4. So this result actually agrees with the conservation of charge. So if, in a way, we denote the quanta of A and B in the following way. So we say that A corresponds to the positive charge and B corresponding to the negative charge. I mean, this indices here, B minus. then you see that the reactions which we have for which we have non-trivial channels are the following. So particle plus particle goes to particle plus particle. So charge is conserved. Positive charge plus positive charge goes to positive plus positive. So 2 goes to 2. 1 plus 1 goes to 1 plus 1. The same is with antiparticles. Their charge is conserved. And then we say we take particle and we take antiparticle. They have an opposite charge. And the transition looks this way. So charge conservation in the scattering process is observed.
Sorry.
Mm-hmm.
Here, well, we don't have the channel that with one particle coming and one antiparticle and 2 particles get out.
No.
Why?
What you can imagine, I mean, because this is 2 particles scattering. Which channel you mean? Say it again.
So that is there's all those discussion of T1 now is just about 2 particles scattering. We don't consider
this is yeah. First of all, we do not assume anything about how many particles scatter. What we say is that we evaluate the S matrix at leading order, and we see that because of the kinematic conservation laws, which are induced by the presence of the integral over x. So I don't impose this conservation laws by hand, not at all. That is the structure of the interaction term. I mean, the structure of T1 tells me that there should be this conservation laws. There should be this delta function. They rise upon integration over x. And then this delta function excludes for me all the terms for which are not neutral. You see here, A plus, A. So if you think that A plus transforms under the complex rotation by exponential I phi, A will transform by exponential minus I phi. So this term here is invariant with respect to this transformation. This term is invariant as well. So here it contains 2 particles and two particle creation and 2 particle annihilation operators. Here it contains 2 antiparticle creation, 2 particle annihilation operators. And finally, in the last term, it contains 2 operators of creation, particle and antiparticle, and 2 terms which correspond to annihilation of particle and antiparticle. So all these interaction terms in T1, they are invariant with respect to the phase rotations, which I indicated for you here. So B and B dagger will be rotating in an opposite way. So B will be rotating as B exponential I phi, and B dagger will be rotating as B dagger multiplied by exponential minus I phi. That's why this A and B will have opposite charge, as people say. And then you see that you can write a general matrix element contains an arbitrary number of particles and antiparticles, but for T1, which has this particular structure, only these 3 non-trivial matrix elements will be non-zero, will survive and will be proportional to the one and the same number. And this result that you get only these 3 channels for the T1, which in fact describes the process of scattering 2 to 2, is compatible with the charge conservation. Is compatible with the charge conservation, is of course, which is of course should be the case, because the interaction term is invariant with respect to these complex rotations. Exponential phi goes to exponential I phi. Phi goes to exponential I phi. how I write it? Phi field goes to exponential I phi multiplied by phi. Like this, and phi star goes to exponential minus I phi multiplied by phi star, making the interaction term in the action, and of course kinetic part and the mass term to be invariant under these rotations. So these rotations, these phase rotations, is a symmetry of our action. And by Noether's theorem, there is a conserved charge corresponding to this symmetry. And this charge you can call electric charge. That's why I'm saying that field phi is charged.
Here it's a U1 symmetry.
It's a U1 symmetry, exactly. That's a U1 symmetry, which is symmetry of the action, and correspondingly, in Noether's theorem is telling you that there is a conserved charge associated to this symmetry, and this you can call electric charge. And so this theory, if you add up to it fermions, you can call scalar electrodynamics.
Sorry, but I still cannot understand why, for example, the term like A1 dagger, B, and A2 and A1 dagger.
No, these are not creation annihilation operators anymore. By this plus and minus, maybe I should take them into a circle, if you wish. I denote particle and antiparticle. Okay. So this is A plus in circle is particle, and A plus is another particle. So this corresponds to a state created by A dagger, A dagger. And this interaction term here, this one, is a term which leads to the scattering two-particle state. So this means particle plus particle. So this is two-particle state here. Particle plus particle goes to another two-state, particle plus particle. And this is exactly this matrix element which corresponds to this transition. A plus plus A plus goes to A plus plus A plus. So particles go to particles. Two particles go to two particles. And analogously for the rest.
Yes, but my question is why this process is not allowed? I mean, from A plus goes to A plus plus A minus plus A minus. I mean, one particle goes into three particles, why that is.
You mean A plus plus A
No,
plus?
no, just A plus. A plus goes to A plus.
Yeah.
Yeah, plus A plus plus A minus.
That's prohibited by conservation laws. That's prohibited by conservation laws. That you cannot have.
By which conservation of charge?
This prohibited not by conservation of charge, but it's prohibited by the conservation of energy and momentum. That I can explain quickly in the following way. So suppose you get a delta function which exactly describes this process. I will write it in a bit different way, but it's equivalent to what you say. K1 0 plus K2 0 plus K3 0 minus K4 0, right? That would be three particles incoming and one particle outgoing. Does not matter what you think about the charge. It's just an energetic delta function. And then there will be, this will be accompanied by the delta function which describes conservation of momenta, like this, right? Plus 3 minus K4. Agree?
Yes.
These are energetic conditions, conditions for conservation of energy in such a process as you indicated, and conservation of momentum. Now take, so what it means? It means that non-trivial configuration exists provided you realize kinematic configuration of this type. And K1 plus K2 plus K3 is equal to K4. If you are able to find such a kinematic configuration, then your delta functions will be realized, and you will get non-trivial scattering. You have a chance to get a non-trivial scattering element which you are suggesting. Now, take a square of this equation. You get K10 squared plus K20 squared plus K30 squared is equal to K40 squared, like this. Now, in addition, no, this is not the end, of course, sorry. I think what I'm saying is that you just square, so you will get also, of course, cross terms. And this is K40 squared, right? Now, you also square the momenta, this equation here. So you get K1 squared plus K2 squared plus K3 squared plus, of course, 2K1 K2 plus 2K1 K3 plus 2K2 K3, right? And you get K4 squared, like this. Now, if you subtract the second line from the first, and use the mass shell condition, and the mass shell condition for each of the particles is the following one. So K0, you should remember that K0 is not an independent variable. Because you solve the equation of motion for a free field, K0 is a dependent variable on K. And there is a mass condition. So this is m squared. K squared plus m squared, right? So this is a mass shell condition. Which is built in a solution for a free field. So this means that if you subtract from the first line the second line, what you will get is the following. So you will get 3 times subtraction from this term, from this, and from this, this. You will get 3 times the mass, so 3 times m squared. And what concerns the rest, you will get 2 K10, K20 minus K1, K2 plus, let's write bracket, K1, K20, say K03 minus K2, K3 plus K10, K30 minus K1, K3. And what you get on the right-hand side is K0 squared minus K4 squared, which is m squared. And so if you put m squared to the left, you will get here 2m squared and here 0. And here you get 0. And then if you wish, you can divide by 2. So you get 0, you can divide by 2, which means that I can drop to here. And so you get this equation. And my statement is that now you can see that every term here in this bracket is strictly positive. And so this equation then never realizes, it has no solution. And why this is positive? And this is for this reason. If you take K0i, K0j minus Ki, Kj, then this is the following thing. So Ki0, Kj, this is a product of Ki squared plus m squared, square root Kj squared plus m squared, minus Ki, Kj, modulus of this. Okay, so this is scalar product of Ki, Kj. I can write as a modulus of Ki vector modulus Kj vector multiplied by cosine of angle between them. cosine theta ij. And then you see that what I can do is I can take modulus of ki squared out of these expressions. Ki, kj, I take modulus out. And then I will be left over with the following expression: 1 plus m squared divided by modulus ki squared like this, square root modulus k 1 plus m squared over modulus kj squared minus cosine theta ij. And you see that this expression here is bigger than 1, while cosine is less or equal to 1. And so the result is always positive, and there is also m squared on the top. And so this kinematic situation where you have 3 particles in and 1 particle out, or other way around, 1 particle in, 3 particle out, is never realized. And so this is the way you analyze all 16 terms arising in the expansion of T1 and most of the terms, except 6 terms, which contain 2 creation and 2 annihilation operators, will be left over. All the other terms will not survive the kinematical restrictions imposed by delta functions signifying conservation of energy and momentum. Okay, do you understand my explanation?
Yes, this one.
Why? Yeah, why this? This happens for the reason which I just explained. So conservation laws do not allow you to have such a kinematic configuration.
So this one is not just as obvious as other previous one.
Yeah. That's why everything reduces just to these terms at the end. These 3 essential terms in this T1. In all the other configurations are kinematically prohibited, but at the end you see that what is left over is also compatible with the conservation of electric charge, nicely compatible with the conservation of electric charge. Okay, I think I finish with this, and on Friday we will have our usual 2 lectures where I will explain the concept, I plan to explain the concept of scattering amplitude and cross-section. And this is important for a comparison of the results of the theory to experiment. Okay, that is all for today.
Professor,
Mm-hmm.
I have one question.
Sure.
So because of the presence of our charged scalar field, so doesn't it compel us to introduce a mu field also, because since it's a charge and
This charge,
field?
yeah. So in principle, if you introduce fermions, then you can gauge this symmetry and consider local symmetry, and then there will be a theory which is called scalar electrodynamics. But I'm not doing this here. I'm just saying that this is global symmetry. It's not local, it's global symmetry, to which you have the corresponding conserved charge. So for me, it's just I'm considering this complex scalar field alone as an example which allows me to understand, or maybe to to illustrate the concept of scattering matrix. Later on, when we discuss scattering amplitude and cross-section, we come to really what's called quantum electrodynamics, where you will have all the ingredients such as Dirac fermions and also electromagnetic field.
So there's in a way we can also say that charged scalar field and electromagnetic field, they all are connected with each other.
Yes, if you want to make this symmetry which I'm discussing here local, then you need to introduce a gauge field. That's true.
Yeah. So in reality, we all have this condition. We have electromagnetic also, and then
Yeah. So in the reality, the field which is of primary importance, or fields of primary importance, these are fields of quantum electrodynamics. So the theory of light and matter, which is around us, that involves such ingredients as Dirac fermions, describing electrons and positrons, and also electromagnetic field, which describes electromagnetic waves and which mediates interactions between electrons and positrons. But I'm using this scalar field, complex scalar field, as an illustration of the concept of S matrix and how to perform computations of this sort in practice. Now you see what is actually I'm doing when I want to compute the matrix element of a scattering matrix in perturbation theory. That is what I have to do. I mean, the computations which you will do in quantum electrodynamics is not different from this, except now your interacting operator will contain fermions and electromagnetic field. But you have to do the same procedure. You expand exponential, you normal order the fields by using the propagators for fermions and electromagnetic field, and you sandwich your result between the asymptotic states which contain now either electrons and positrons or both together with photons, together with asymptotic photons. And then you can compute various scattering processes. For instance, scattering of electrons on positrons, scattering of electrons between themselves, scatterings of electrons and photons, so Compton effect, and so on.
Could you please explain the meaning of the terminology on shell and off shell?
On shell means that the fields solve the Klein-Gordon free fields solve their equation of motion, which is Klein-Gordon equation. Box m squared on phi is equal to 0. In momentum space, that equation reduces to k squared plus m squared on phi on k is equal to 0. And solution to this equation then is given by phi on k is given by some, how we write it? We are writing some, no, let's write here phi. Multiply by delta function on k squared plus m squared. That's right, k squared minus m squared. And then this means that non-trivial solution will be only on shell in a sense that this condition k squared plus minus m squared must be satisfied. K squared is k0 squared minus k vector squared minus equals to m squared, or if you wish, k0 is equal plus minus square root of k squared plus minus m squared. And that's what means on shell. On shell means that field phi satisfies its equation of motion.
The free equation of motion.
Yeah, free. Because here I'm talking only about free fields. You see, again, that's a nice feature about this perturbation theory, is that at the end of the day, everything reduces to the computation in terms of free fields. Because
and off shell?
Off shell, that is a different story. So off shell theory, it means that field is not satisfying its equations of motion. And there is such approach which relies on this, on off-shell fields, and this is a path integral, where integrating over all fields, not only those which solve classical equations of motion. Okay? That would mean off-shell. Off-shell is field is not satisfying its equation of motion. On-shell means that it satisfies its equation of motion. So,
and the
these
second
fields,
question,
these fields which I'm using just to finish here, for instance, these fields solve their equations of motion. And that's the reason why this omega on k does appear. This omega on k, omega is precisely this square root k squared plus m squared. And it does appear because these fields, if I now apply to this field Klein-Gordon operator, so the result will be 0. The result of this will be 0. Because when I apply the Klein-Gordon operator, I differentiate twice with respect to time. So omega squared gets down. Then I differentiate over x, k squared gets down. And so at the end of the day, I will get here omega squared minus k squared is equal to 0, but omega is written as the square root, k squared plus m squared. So I exactly reproduce the mass shell condition, and I just get 0 when I do that. So these fields which enter in this expression, they are solutions of the equations of motion.
And the second question here, we have a conservation of charge, which is not electromagnetic charge. And
no, this is just
in general
symmetry.
Yes. And in general, is it true that to every conserved so we have Noether theorem, which says that to every global symmetry corresponds a conserved charge.
Yes.
Is it true? Is the converse true? Like, is every charge, is every conserved quantity corresponding to some? Does every conserved quantity correspond to some symmetry?
Not really, because you might have discrete symmetries which do not have conserved charges. For instance, well, you have a parity, for instance, right? But you don't have a continuous symmetry which corresponds to it. Other way around. Okay, I put it other way around.
Yeah. I mean, it's obvious that the Noether theorem doesn't work for discrete symmetries. But is it true that to every conserved quantity corresponds some symmetry?
But I mean, again, I mean, if you have charge, I don't know how to say.
For instance, lepton number and baryon number.
Yes, you have the corresponding conserved charges. Yes. And typically you have the corresponding current which corresponds to the Noether theorem. I mean, which comes from the Noether theorem. Yes. So I would say, I don't know, if, for instance, you talk about such things as parity, you cannot write an expression for this charge because you don't have behind the continuous symmetry which would produce you by Noether theorem such an expression. Nevertheless, you may say parity is conserved. So interactions are parity invariant. But I think you cannot write...
Shouldn't parity be conserved because the Hamiltonian commutes with the parity operator?
Yes, but I mean, there is no discrete symmetry for that. So parity operator, parity is like a discrete transformation. You cannot produce any other charge for it. So you have something which is conserved, which is commutes with a Hamiltonian, but it's not coming from the Noether's theorem. That's what I'm trying to say.
Okay, so the converse is not true.
Yeah, so it looks like converse is not true because you can have some operators which commute with the Hamiltonian, but you cannot really write for them the corresponding expression from the Noether because simply there is no continuous symmetry behind. The symmetry is discrete. Yeah, so the answer
Okay,
is
thank
it
you.
works in one way. Moreover, I could add to this that actually the symmetries of equations of motion are larger than the symmetries described by the Noether's theorem, or maybe larger than the symmetries described by Noether's theorem. Because there could be symmetries which are symmetries of the equations of motion, but they are not, as we say, variational symmetries. They are not symmetries of the action. So they transform solutions of the equations of motion to solutions, but they are not coming from variations of the action. They are not coming. They have no relation to the Noether's theorem, because Noether's theorem tells you that you need symmetries which leave action invariant. No, maybe up to the boundary term. And such symmetries are called variational symmetries. But the symmetries can be larger than those which are variational.
Oh, such symmetries also don't produce conserved charges.
Yeah, such symmetries do not produce conserved charges. It is true that any variational symmetry is a symmetry of equations of motion, but the inverse is not true.